Hello everyone. I am Priyabrata again, and I am the co-founder and director of IIREES. Today, me and my junior, Dr. Subham Sarkar from PRL Ahmedabad, he is a planetary geologist, will host you the today's session. As you know, IIREES is a India-based education and research initiative that aims to build a new generation of creative, passionate, and critical thinking natural scientists through transformative education and research support. Art and Planetary Science Seminar Series comes under our core activity. So far, we have organized seven lectures on various domains of Earth and planetary sciences. And and if you have just somehow missed those lecture, you can just go through our YouTube channel and watch all these recorded sessions. Today we are delighted to have Mr. Arka Das from ONGC Ahmedabad, India, as our esteemed guest speaker, and I'm welcoming him also. So far, we have received a fantastic response from all across India and as well as global different countries from across the globe. And I thank you everyone from IRIS. If you have any questions, feel free to ask in the chat box. And during the seminar, please turn off your microphone off and please turn off your videos also. So now, without wasting much time, I would like to invite Mr. Shubham Sarkar to host the session. Thank you. Thanks for joining today. Shubham, now the stage is yours.
Thank you, Dr. Dash. It's my delight to introduce Mr. Dash, who eventually my classmate from BSc days in Presidency University, Kolkata during the year 2011 to 2014. So we had so many memories together. Apart from studying geology, the basic days of studying geology, we played cricket, we played cards, and all those things, and learned geology together. And then eventually, Orko went to IIT Roorkee for pursuing his MSc in applied geology with a master's thesis in structural geology, and completed his master's in 2016. And at that year, he joined ONGC, Oil and Natural Gas Corporation of India, and worked. Is working there for the last 6 years as a senior geologist, and now he's currently posted at the forward base here at Ahmedabad. So his current role is to monitoring of drilling, logging, and testing operations in exploratory and development wells, collection and analyze of well-related data, and coordinating with well site geologists as well as other disciplines for the smooth decision making, and also preparation of well completion report and exploratory developmental wells, making correction profiles and identification of pay zones from the well logs. And not only that, it's his current role assigned by the company, but he also had some interest, some research and academic related interest, obviously related to his current job posting or current job role, that are the seismic interpretation and basic modeling, both structural and stratigraphic, and also interpretation of different advanced logging techniques like FMI, wave sonic, NMR, ECS, etc., and also in petrophysics. And also, last but not the least, the integrated study of combining geology and geophysical data from micro to regional scale. So a fascinating career, I would say, for the last 6 years. And who else we could have to hear about the exploration of petroleum rather than Orco. So I think we all have enjoyed yesterday's talks, where Dr. Shandip Roy just talked about the basic philosophy of exploration, but that was not about only related to exploration. Any field of science or social science, people could find it interesting. Unless you are not watch the video, or you are not you are absent, please visit our YouTube channel to visit that. Obviously, after watching this, over to you all.
Thank you, Shubham. Thank you for the introduction. It's a bit too much for me. Actually, I'm still. I left my college in 2016 and joined ONGC. But I'm still a student by heart, and I'm still learning a lot many things. And I'll probably be learning for the rest of my career as well. So I'll just. It's not a talk that I would like to say. It's not a teaching or some lesson kind of thing or a seminar about. I think it's a, we should say, a knowledge sharing session. So I just keep it simple, and I'll just start right away. So yeah. So the screen is visible, right, Shubham?
Yes, perfectly feasible.
Okay.
You can go to the full screen mode. Yeah. All right.
So I have chosen this topic, deciphering the subsurface using multiscale geological data to understand the petroleum system. Ideally, it should be a vast, very vast subject, and there are a lot of discipline that works with. They are not only geologist and geologist, geophysicist, reservoir modeler, geochemist, and I would say production engineers. All of them together, they built a team to decipher the subsurface, not only GNG public, GNG team or geoscientists. So I have chosen this subject, but I will keep my focus on the geoscientist aspect on the subsurface. All right. So I'll keep my contents like this. From introduction to basic concepts and data from regional scale to micro scale, as you accurate, interpret it, and then use it in a model, and what to do with all this data, and how much data we require, how much data we should acquire from exploration stage to maybe a mature stage of a field. Then summary, and then I'll accept questions from you. So I'll begin the presentation with the notion, where Wallace E. Pratt, a famous pioneer petroleum geologist, he said that oil is found in the minds of men. Uh, you can find this quote very fascinating, and I have also found some twisted versions of this saying that oil is found in the mind of geologists. That's not true. All since all the disciplines and all the minds are working together to build a subsurface model. So let's just keep it that way. So we'll all need to think like that. Before science and before technology, all we need is creativity, as Dr. Sandeep Kumar Rai has already said in the earlier seminar of this IIREES presentation. So we need to start somewhere. So we need an imagination, right? So without that imagination, the whole concept is dead, the whole model is dead, and there is no oil. And that's the truth. So saying that, I will go to the basic concepts of key elements of petroleum system. You might all know about this petroleum system in a very similar model. You can find it in textbooks and on internet. So we'll start with source rock. Source rock is a very fine-grained rock, organic rich and thermally mature, that will produce the hydrocarbon. And typically it's a shale, and maybe some other fine-grained rocks are claystone, but it should be fine. And the only two requirement to be a source rock to be oil bearing is either one, it should be a organic rich, and second, it should be thermally matured. Moving on, we have a reservoir rock, which is porous and permeable rock. Any kind of rock, including this shale and hard rocks, are reservoir, can be considered as reservoir rocks. Okay, because porous and permeable are two petrophysical properties or the framework properties of rocks, and it's not only the sedimentary rocks that are acting as a reservoir of current days. because people are finding or targeting, rather I would say, reservoir rocks in granitic basement or basaltic basement, which are all fractured. So it's hard to think that we will find much more oil in much more oil in igneous or metamorphic terrain, but it's not true. So any kind of rock technically can be acting as a reservoir rock. Okay. So then following by reservoir rock, we have a cap rock, which is non-permeable again. Uh, we have an entrapment mechanism. So it's not, you can think of it that these are the key elements, but the source rock, reservoir rock, and cap rock, these three are lithologies, right? So these are physically, we can touch them, taste them, smell them if we have the sample, and we can assess them as the body of the earth. Okay. But entrapment is a configuration or state setting. It's like the distribution of the rocks in the subsurface and how they are occurring in the subsurface. Following by entrapment, we will need a migration process. This is a process and hydrocarbon movement from the source rock all the way to the cap rock inside the reservoir rock. So without the migration, we won't have a oil pool here. So we won't be having any oil pool here, because if say for example we have a source rock, reservoir rock, and cap rock all in this order and no migration, then technically if my source rock is mature enough, then only it can release the hydrocarbon to form a pool, right? So another most important element here is the time or order of events. So we'll discuss one by one, but first I will focus on the definition of a rock, which is a naturally occurring solid mass composed of aggregate of minerals and mineraloid matter. Okay. So crude oil, we can say naturally occurring mixture of hydrocarbon. I am just defining the rocks and crude oils are here, but another two major ingredient of the surface is the water and maybe gas, which can be similar description, which is the similar description of crude oil as well. So why I'm focusing on this? Because these are the major components of the subsurface for a petroleum geologist that they should know. I will focus on these two words here. One is aggregate and one is mixture. The definition does not define the ratios or proportion of these minerals together or the hydrocarbons together. So technically, we have a wide range of compositional ratios or proportion inside the subsurface. Practically uncountable number of permutations and combinations of ratios of these individual components, right, to form this rock and or this crude oil. Together with this, we have wide range of natural distribution at every level. It gives us a reservoir heterogeneity model at every possible scale, from micro to macro to mega to giga. So you can see, if you can see the image right here, from micro scale, we can have some heterogeneity inside the grains, inside the pore networks, and inside all the fracture networks. Then we come to macro and mega scale, and all the way to giga scale. All we have is heterogeneity. Our reservoirs are not simple as we think it is, right? So we need to model them, we need to study them, we need to build a feasible understanding of the subsurface to explore for oil. So moving forward, so I have prepared a scale. You can see in the right corner, we have this 1 micron scale all the way to 1,000 kilometer scale. So we acquire data in exploration point of view from regional scale all the way to micron scale, from left side to right side. So the first and foremost data we have from to understand the reservoir or to understand the subsurface, I would say, is the reconnaissance surveys, which is conducted on the surface. So we are basically understanding the subsurface from the surface surveys. So these include gravity survey, we can say magnetic anomaly survey, and we can say that remote sensing survey that provide us the basic data set of or a basic idea of what our surface is looking like and what our subsurface should look like in the Earth's crust, right? So following by that, we have a geological map. Everybody is aware of the geological map. It's basically showing the contacts, the strike depth parameters, and all the possible lithologies that we encounter on the surface. How do we create a geological map? Lots and lots of data points accumulated from outcrop analogs or outcrop surveys. You have no outcrop surveys, we have no outcrops out there, so we don't have any map of the subsurface, what is beneath, from the geological map, right? So whatever is on the surface can be plotted in the geological map. And then following by that, we have seismic. This is the most important and most crucial data in oil exploration. And historically, it has proven very accurate in terms of both scale, both spatial scale and both vertical scale, to understand the basic subsurface nature of a particular basin. So we can have all the surfaces that we need, all the surfaces in terms of sequence boundaries, all the surfaces in terms of the fault boundaries, and also the beds, and sometimes the salt diapids. So all the basic information you need for structural and sedimentological information comes from the seismic. The basic, not the advanced one. Then from the basic understanding, if I delineate my basin right here, and I need to explore further, so I have to drill exploratory wells, because I need further data to assess the subsurface. These are just outline of my framework. This is the framework of the subsurface, and these are not the entire picture. So I need to prove, or I need to feed data to the system to more accurately get the entire image. So we'll drill well, and this part of from 1 meter to 1 micron, we have the set of data which is acquired either from logs or from the physical rock samples like core data, drill cutting, sidewall core data. We process the data in the lab, and we get thin section and SEM studies. And further moving on, if we have nanoscale studies, that as well. So this part, the upper part, shows the indirect data, which is the geophysical surveys, and the lower part is the direct data, which we acquire from the direct rock sample. So all the data we have here, we need to collect them, and we need vigorous quality checks at every possible scale. And then from there we need to interpret this data and to link them to build a feasible model. That's our task, right? So moving on, I'll just briefly discuss one by one. This is a regional geological mapping. So we have the basic rock types, basic structural details from the basin. So now I am working in Ahmedabad in a it's called Cambay Basin in India. So it's a rift basin, basically. It's a aborted rift, the western subcontinent part of India. So in this geological map, I cannot see Cambay Basin's general outline or the subsurface position of Cambay Basin in this geological map. Why? Because we don't have any outcrops of the rocks that is forming the Cambay Basin. Okay, this light yellow colored part is the quaternary rocks. So from this geological map, I have a certain amount of idea that these are the highlands, these are the Deccan traps, this is Aravalli right here. These are the highlands surrounding the Cambay Basin. This part is actually the Cambay Basin outline. So there are deep-seated faults. There are layers of sediments, Cenozoic to all the way to Deccan traps, and beneath that maybe Mesozoic as well. But I have no idea how the subsurface of Cambay Basin should look like from this geological map. It is not true for all the basins. Since it is covered by a very vast thickness of quaternary sediment, I cannot have a trace of Cambay Basin from this geological map, right? So we'll have this igneous and metamorphic rocks everywhere, and we'll have this sedimentary rocks and depositional environments. We can take analogies from this model and place it in the subsurface in the later stage, but that's a different story. But right now, what we have is a geological map with some outcrop features here and some structural features like faults, faults lineaments, and nothing else. So we'll move to the next model, which is regional geophysical derived from regional geophysical surveys like gravity anomaly, magnetic anomaly, surface resistivity survey. So these are also surveys that is carried out on the surface, right? But we have some interpretation of the Earth's crust from these surveys, or we should say we can identify the basement highs and lows and buried mineralized zones or deep crustal anomalies from this. But we don't need this layered sediment of a kind of thing. Only when we have a high contrast of the density or high contrast of this magnetic anomaly, then only we can see this data, right? So it is helpful, extremely helpful for delineating the basin structure or the sediment thickness, I would say. And this regional dynamic modeling is all we can get this regional scale geophysical surveys. Moving further, we have seismic surveys, right? So here is a map in the inset of Cambay Basin, and there's a tiny little line that is across the basin margin, towards the basin center, right? So this seismic section is showing the east-west configuration of the basin with all the seismic reflectors here. This is the interpreted data, right? So we can delineate subsurface reflectors. And by reflectors, I mean that this is a map of the surfaces in the surfaces which is seated in the ground below. The reflectors are formed by impedance. Impedance is a property of the rock or a layer, which is velocity multiplied by density. And we need to have a contrast to delineate this impedance. If we have two layers which are having a very close impedance values, then we will miss this surfaces in the seismic survey, right? So the basic understanding from the seismic survey is that the stratigraphic framework and the fault models. You can see we can see the fault lines here. We can see a series of half grabens. We can see a highland here. We can see another series of half grabens towards the west. So this is how a rift margin should look like, right? A rift basin should look like. Internally, we can further subdivide the layers into some sequences or maybe some other features. These are the, in this model, they have linked this model with this tectonic events. Okay, so this peak sin rift and then early sin rift and late sin rift, early sack phase, late sack phase, post rift, all these things are interpreted in these layers. Without this color code, all you could see is this like this image only. So it's an interpreted model of this. And the first 3D volumetric impression of the subsurface comes from the seismic always. Because if you don't have the first impression, we cannot go further, and we should acquire the seismic image first and then go for the drilling, because otherwise we'll be drilling blindly, and that will yield no result to us. The only problem of the seismic image is that if the vertical resolution is 10 to 30 meters, it's 1/4 of the seismic wavelength. That is again 40 to 250 in very generous case. And so any feature, any impedance contrast beyond this 10 to 30 meter depth, 10 to 30 meter thickness, it will be missed in the seismic image, right? And the resolution gets poorer and it greater depths, and the sediment as the sediment get more compact. So in the greater depths where the sediment is highly dense, the velocity will be too high. It will have great impedance values. The seismic waves will attenuate, and you will not get not much reflector as you are getting in the shallower parts. So these are two major drawbacks of the seismic image. Other than that, the seismic image is the only thing we need right now to get the first impression of our subsurface. Moving forward, this is a section of that earlier seismic image. We can delineate the different parts of the basin. This is Olpat, OCS, Vaso, and in our case, this is the Kalol formation. These are formations which have significant impedance contrast all the way to the surface, right? So we can mark these horizons as our formation boundaries, and we can choose our suitable spots to drill. Like I am seeing this reflector is going down towards west, right? So this is, so somewhere here we could expect highland, and if I need to explore oil pool here, so I'll go for the upward direction like this one. But we need to have confidence in our data, and we need to have very high contrast of impedance to delineate these surfaces. Moving forward, from the seismic data, we identify our spots to drill a well. We have then a series of geophysical properties obtained from well logging data. I'll start by conventional logs. So we have a series of log in a conventional logging set. We call it a triple combo or quad combo, depending what kind of data are you acquiring. So starting from gamma ray to resistivity to neutron porosity to bulk density and sonic. So what these logs do, we have a tool, we run it inside our drilled borehole, and we start recording the geophysical properties while pulling out the tool from the borehole. So the basic natural gamma ray, this is the most important logs in all sets of well logs here, because this is a very useful for correlating different well profiles, right? What this gives us is a shale volume or a clay volume if we incorporate in a formula. So this is not just a correlation logging. This is not, because we have a general idea that the higher gamma ray should come from a higher clay-rich mineral zone. Clay-rich zone. Clay-rich zone means either it should be a clay stone or a shell. Not always, because we have a higher amount of gamma rays coming from the heavy mineral deposition zones from sandstone as well, right? So in general, if you have a clastic reservoir, we can expect that the shale horizons will give higher gamma ray than the sandstone horizons. Moving on to the next log, we have resistivity, again the most important log, and probably these two logs alone can interpret your wellbore. Okay, we don't need any of this. The old classic logs are only consist of gamma ray or probably SP logs as well, and resistivity. Resistivity is a must. Resistivity is a must in every borehole, because it provides you the internal fluid saturation structure, right? So we have formation resistivity. We can translate this data into water saturation from Archie's equation. Further, we have these two logs are very important for density and porosity point of view. So these neutron logs are basically the purpose of these logs are to delineate hydrogen index. This is not exactly porosity, but we can translate into porosity with some equations of petrophysics. And then bulk density. This gives us just the bulk density regardless of the fluid inside. Just all the fluid and the framework inside, we can get the bulk density of certain horizons. Then we can have sonic log. This is also very important. This measures the wave slowness of different wave. We have compressional wave, we have transverse, the shear wave. So this wave slowness varies in these different zones, and we can get an idea of porosity, and as well as these are basically geomechanical properties of the well of the horizons. So we can get that from the sonic log. So the gamma ray resistivity and neutron density and neutron porosity and bulk density together, this will form a triple combo log. This is a very essential for every well drilled in a basin, and you can add sonic into that. You can get a quad combo log. Every log has their own depth of investigation and their resolution, vertical resolution. So this image actually shows the different logging, different log tools and their resolution vertically as well as horizontally. So But basically the standard log data is coming from a 6 inches interval, which is probably this much. Anything beyond this 6 inches will be masked by the average data above and below, right? So log data has its own constraint, but 6 inches interval is also a very good resolution in subsurface. Indirect mode of identifying lithologies. Yes, they don't tell you lithologies right away. You have to interpret with this data, and you have to have various solvers, various equations or models to feed those data to get the lithologies. Generally, logs are interpreted in forms of combos like triple combo or quad combo, right? You cannot interpret any lithology using one single log. I can have this entire column of gamma ray logs, and I cannot tell, say for example, I don't have this resistivity and neutron porosity here. It's very wrong to say this is a shale part and this is a sandstone part. Is very wrong. We have to combine all this data to resistivity data and as well as a neutron porosity and bulk density. Together, they will tell how the lithology is changing in the subsurface. Okay, where the water bearing zone, what the oil bearing zone is. By the way, you can see there is a crossover happening in this part. We can have a crossover happening in this part with high resistivity and less gamma. This is a probable zone for hydrocarbon saturation, right? And compared to this is also a less gamma and crossover zones here, but we don't have much resistivity buildup here. So we can interpret this as a water saturated zone. We have coal horizons here, drastically reduced Zn or the density or the N5 logs or the porosity logs. This will go beyond the negative values. This will go beyond the negative values. These are the coal horizons 1, 2, and 3. Okay, so and all other things are probably shale, which has higher gamma signatures and almost flat-lined. This part is shale, a lower resistivity signature, and this porosity and density curve are not touching each other or crossing each other. So this is a reverse crossover. So this is a shale zone. This part and maybe this part as well. We have higher density signature for the shale and lesser density signature for the sandstone parts. So this is a basic log interpretation that we gain from the conventional logs. How to use it further? Then we have some basic formation evaluation and petrophysics equation here. If we have a clean formation, we can use the famous Archie equation. You can see the not much parameters are here that you can play with. You have RT. RT is basically this part. You have RW. RW is taken from other logs as well as experimental values. We have a coefficient called A, M, and N. All these are considered a constant from different parts of the basin, or I would say a different part of the field. These values are constant, A, M, and N, right? These are exponents and constants. Porosity, we can get it from either from the sonic log, or we can get it from the neutron log directly. And we get SW, Archie. SW means the saturation of water. Why do you need it? Because a general understanding is that our subsurface is a combination of rocks and fluids. Fluids can be either hydrocarbon or water, nothing else. So once we get the water saturation inside the pore space, we can automatically generate the hydrocarbon saturation from the simple equation 1 by the saturation of water, which either we can get from this Archie equation or we can get it from Simando. Simando is another equation to delineate the non-clean version of the reservoirs or the clay-rich version of the reservoirs, which is not typically a clean sand or good sand. It's a mix-up of sand and clay part, and all the highly radioactive minerals or clay minerals are there. So we have this V shell is here. V shell is calculated from gamma. RT and RW I have already discussed. R shell is an experimentally deduced value, or you can take it from log from a pure shell. Then porosity, then V shell, R shell again, A, then M, and then we have a root over of this parameter, and we can get this is a more complex one because we are taking into account this shell proportion or clay proportion here. But anyway, we are getting this saturation hydrocarbon from the saturation water, this equation. From that, we can generate a basic equation OOIP, or the original oil in place. This is a formula of a volume. This equation is mother of all petrophysical equations, and everybody in the upper management, or I would say everybody in the business level who are operating the business, is wanting to know about, because they will not listen about this RW, RT, this gamma, resistivity, and whatnot. They will need a significant amount of they will need the volume of hydrocarbon that is trapped below, and this is coming from this equation. We have area, we have height. These two parameters, when multiplied, gives you the volume. We have the bulk volume, and this is the porosity we can get from the log. Again, if you multiply porosity inside this, you have the idea of the void space inside the subsurface or any layer. And then we have this hydrocarbon saturation from 1 minus SW curve. And then divided by this, we have a formation factor, or formation the oil factor or formation factor. This is a ratio between the ratio of the values, the oil which we estimate in the subsurface, and oil which, when produced, when it comes above the surface, the values can be different. We take the ratio and we take as the denominator of this volume function. So this is the equation where the science meet the business. Okay, so all in the equation is telling you about this oil in place. We can generate much more complex equation from this, but this is the basic equation. Moving further to that, we have special logs. We have NMR logs, which gives you a permeability and porosity. By the way, these are all logs which we need to study for a special evaluation of our subsurface. Okay, quad combo and the triple combo are just enough for any kind of routine survey. But if you need to study further, if you need to acquire more parameters from your subsurface, then you will need to have more data from different sources. So we have nuclear magnetic resonance, or NMR. From here we can understand, I will not go into the details. This yellow part are giving you the permeability of the different layers. Okay, these yellow parts, wherever there are these green parts, these formations are dominated by these green parts and this gray part. These are basically the shale volumes. These are actually the horizons where you can produce your fluids, or I could say oil. Combined with this, we can have dipole, sonic, or anisotropy. This is as simple as the sonic law itself, but it works in three-dimensional way. We have the compressional waves as well as the shear waves in different direction. You combine them and you get the anisotropy in the vertical level as well as the horizontal level. You can analyze the fracture networks in the borehole. Following this log, we can have elemental capture spectroscopy. This is a useful log for analyzing your subsurface geochemically. The log gives you different proportion of dry weights of the major and minor elements, starting from silica, titanium, aluminum, potassium, ferrous, manganese, and this calcium, and probably sulfur. We plot them in the depth column, and we get where the silica is rich, where the iron is rich, and probably where the aluminum is rich. You can see, not surprisingly, it's actually very correlable with the gamma log here, because we have the gamma log actually represents the clay volume or the shale fractions of this subsurface. You can have higher aluminum content as they are associated with clay minerals, right? These horizons are coal horizons. These are, although there is data, they interpret as clay horizons. And then we have most fascinating logs in the series. We have this formation microimager. This is an image of the borehole itself. The image is not optical, it's combined effect of it's a combination of a directional tool which can give you the strike dip data as well, and this resistivity data, right? So this image is painted by contrasts of resistivity. So this part is presented here. We can have this coal horizon. We have very brighter resistivity value against that. So this is a three-dimensional data of the borehole itself. This is a proxy for any conventional core you can take from the borehole, right? You can see multiple layers, multiple structure. This is a very fine scale rock, fine scale. This is log, and we can get the three-dimensional aspects as well. We can have the deep data along these horizons, because we are literally seeing the borehole when cut open. This borehole from 0 to 360, we are just placing them in a piece of sheet, and we can get the surfaces in the 3D, right? You can see some amount of resistive clast floating inside the clay horizon, which could not be distinguished in this log or this log on this log, or the triple combo or quad combo. So this is a very useful logs for petroleum exploration. From these, we'll move to regional scale to micro scale. This is mesoscale data. Mesoscale means this is lying somewhere between your log scale to or more finer scale data. This is a core taken from a borehole, right? We can physically touch the sample, physically evaluate the sample. We can run tests on them and get the parameters. From this image, we can get this is a coal horizon. This is basically the orange parts are basically sideritic cement rich horizons, and the rest of the parts are mostly shale with fine laminations or lenses of this sandstone layers. Now this is a 1 meter interval, right? Your log scale will average out every data point in 6 inches. So basically what will happen, you will miss this fine scale structural and sedimentary structures in the log scale. You will never get that. So unless or until you can get a core, your idea of the subsurface from only from the geophysical surveys will be incomplete. Okay, but there is a constraint. We cannot core down the entire borehole because it's very lengthy process. It's a one core is generally 9 meters standard. We can take 18 meters core in a well in a single stretch. It's very costly affair, and it's very time consuming, and it's not always necessary. So wherever we can identify a zone where we need to study the reservoir further, or we can need the source rock information, we can core there. We can have core in multiple wells in multiple segments, and then we can connect them with the well log data, and then understand how our subsurface looks like. From routine core analysis, we can get basic hydrocarbon show evaluation from UV light. You can see this under UV light. These sand horizons, which are actually oil bearing, this glows in the UV light, and we describe them as either golden yellow or dull yellow or pale yellow, depending on the crude oil quality. So this will the plain light, and this is the UV light system. And other than cores, what another physical data we can gather in all wells is the cutting sample analysis. So cutting sample is much more smaller than a core sample. This is 1 meter, and this is a 1 centimeter sample of drill cuttings. This is basically we cannot do this on every this is a not very fine-tuned analysis, I would say. This is averaged from a 5 meter or 3 meter column as your convenience. So whatever is happening, this is a 1 meter interval for your reference. So you add another 2 meters here or here. So whatever happening, this entire core, if you chip it in a very fine grain chips, you will get a core sample. You will get a cutting sample like this. We evaluate them routinely under microscope and also in this UV surveys to get a basic idea from them to identify the lithologies. This is a water bearing sand. This looks very white, and this is oil bearing sand. Only this much will be enough to understand whether it is sand or shale or the basement rock fragments, or it's a clay stone, or it's calcareous or not, whether it's having coal chips or not. So this is a very basic understanding we can get. And because drill cuttings requires no additional effort, drill cuttings is a byproduct of drilling itself. Okay, every well that we drill is automatically giving us drill cutting. We just have to collect them, we just have to wash them, and then we can have a full percentage log of these lithologies. Yes, of course there will be errors because we are taking this at every 5 meters interval. Data will not be correct, it will have some contaminations in it, but it's as good as having a core sample where there is no sample at all. Okay. What is the resolution of these drill cuttings? It's you can see this 1 centimeter. So anything beyond 1 centimeter or 1 millimeter will not be recognizable in the cutting sample. So we'll not get the intricate structure or their arrangement inside the borehole, but we gave it gives you the lithology, and that is good enough, right? Because it's a physical sample, you can actually check this with the log whether I'm interpreting a shale right or whether I'm interpreting a sand right or a carbonate lithology right. So this is a good enough data. So we can directly identify the lithology and hydrocarbon assessment from our drill cuttings and core samples. Okay, it should be examined further in labs for advanced analysis and measurements. We'll get into that. So basically what we can get is core and cutting sample is a geological data. We can get lithology, we can get structure, micropaleontological studies, palynological studies, and mineralogical studies, right? From petrophysical aspects, we have porosity, permeability. We can plug the cores in different intervals in our point of interest. We can run the experiments on them, and we can actually get the porosity, permeability, grain density, fluid saturation, capillary pressure, core gamma, electrical properties, X-ray and NMR, all from a physical sample of core, right? We can then calibrate and validate all these data with the conventional logs or the advanced logs to check whether the data is correct or my data is affected by some other parameters in the borehole. Then geochemical aspects, we can have source rock evaluation. We can have a whole series of experiments. We can run rock eval pyrolysis, and then liquid chromatography, gas chromatography coupled with this spectroscopical analysis. And then we can have vitrinite reflectance. We can assess them from samples that are coming from both cutting and cores. Okay, we don't need much sample out of them, but for source rock evaluation purpose, we believe the only thing we need is the physical sample, and that comes from your core and cutting samples. Moving on to that, we can chip them, cut them, and polish them into thin sections and electron microscopic study. This is just a representative of the sandstone and siltstone intervals, where we can get a basic idea of the grain frameworks and the clay mineralogy. From this part, you can have kaolinitic clay or intergranular porosity, very higher resolution scale in the ACMs. We can have EDS spectra. We can have this X-ray map of the pore networks, all from this physical samples. Thin section studies actually is good for identifying the cement types and the clay types and the mineralogy, whether we are assessing it right or not from the logs. These are good for that. We don't need to do that in all intervals because it's pointless, but we can have a reservoir and we need to assess that for further study. We can do it only then. Moving on to the same picture. So if we started from seismic, or rather we started from a geological map, then all the way up to seismic, okay? And then we straight out of the seismic, we jumped on drilling a well, gathered a petrophysical data set from well logging data from all the way to core and drilling, then thin section and SEM. This is the basic workflow of data gathering and data acquisition. Outcrop analogs are not always possible to get because you have to have outcrops for that. Not all basins have physical outcrops in the surface, so it will be missed. As I discussed earlier, it will be missed in the geological maps. So for now, I'm keeping outcrops from the image. This this generalize the whole data set into two types of data. Either we have a seismic data in 2D or 3D model, or we have well data. So this is all we have. You can see, surprisingly, we have nothing in the 1 meter to 10 meter space. Okay, so generally seismics are actually volumetric data. Seismics I can stretch this image up to this 100 meter or even further, but it will not help me identify the subsurface because seismic data's resolution is poor. So it's good for interpreting a 10 kilometer or further that, or 1 kilometer or further that, but not in this space. At least we will be wrongly deduce our surfaces in this space. So this is a data gap here. We don't have anything acquired from either of these surveys or these well logs and this well logging data, because you need to understand this well data comes from a borehole, which is either a 12-quarter borehole or a 8.5-inch borehole. This much cylinder we are talking about, this much of hole size we are talking about, this much. So we get all this data from that part of the subsurface which is exposed to the borehole. So this is a data gap. So how to fill it? We need to drill more wells. More wells will give us more data, meaning we have a seismic, we have a basic understanding of one well. We need to drill more and more wells to expose the subsurface. We need to check whether the seismic is correct, whether the surfaces are placed right, and whether our model is validating or not, right? So these two are mandatory. Seismic is obviously mandatory. Well logging is obviously mandatory. These are not always possible as well, but we need them as validation of our existing data set. We need to check whether I am correct about my sandstone, whether I'm correct about my shale or limestone, and whether I'm correct about the porosity data or the clay mineralogy. We can get them from different types of well and from parametrics well, which are solely or exploratory wells, obviously. So which are generally for data gathering purpose. Otherwise, in development wells, we don't generally go for coring and this cutting sample analysis. So moving further, what to do with all this data? We need to correlate, we need to integrate, and we need to build models. Okay, so what do we do when we have a correlation profile from this data? We have data integration, interpretation, and reservoir scale model. So all the way from this, we need to integrate all kind of data here, interpretation and reservoir scale model, and then a basic understanding of subsurface will rise, and from this we will do our further exploration or further production from these models. We can get some crustal understanding from this part, from 10 kilometers to 1,000 kilometers. We can have some understanding from this petrophysical data, petrology and flow model and mineralogy. We can get some understanding from the source rock evaluation and geochemistry, some understanding from the pore network map and grain fluid interaction from the micro scale to for the nanoscale data. What we do all this, we gather this, we fit them in a data integration model. Then we get a static geological model or dynamic geological model where you can see all the processes rather. Then we have reservoir simulation model, and we have another model called migration model. We can actually see the oil migrating from source to reservoir. So let me just quickly finish my seminar with an example. This is a correlation from two wells. Say, for example, we have well A and well B. If we are solely dependent on this well logging data, suppose this is well A, where we have some data generated from here. We have some sand identified, sand A and sand B. We have a well B. Same sand, or I would not say the same sand, but I interpret it as the same sand, A and B. So I'm happy with my result. And if I need to drill a third well, I make a correlation profile across this gap where I need to drill another well. So I connect A to A, B to B. I drill a well called C, and surprisingly, I have no sand developed here, no sand developed here as well. So how is this possible? Is my correlation wrong? Yes, it is wrong. So is my understanding wrong? No, understanding is not wrong. I would say we need more data to fit the model because we have a lack of data. So we have a missing gap. So with the well C, although it's a dry well in terms of oil industry, we have a set of data which shows no signs of sand here. But now we can refine our model. This is a dry well, but it's giving you some data, right? So what is that data? We need to interpret this in various ways. We can have a scenario one. We can have a fault model when the fault is just cutting through the well C, and we don't have the exposure of A sand and B sand, although they should have been connected. Because there's a fault acting between them, we don't have anything in well C. We can have this scenario as well, where A and B is not equal to this A and B. I am calling them now C and D because these are not connected sand bodies at all. These are dispersed sand bodies in a shale framework. So we can have A, B, E, C, D, E, F, F. Multiple sand lenses are here. So you can miss one of them. It is very common where the geological model actually depicts the different sand layers here. We can go to the next possible scenario, which is combination of both. This is more dangerous and more difficult to predict because we have the lenses as well as we have this fault acting here. So we can never reach to the sand C, right? A and B we get from here, A and C and D we get from here. We have some different properties here, we have some different properties here. We can never get E because the well C will not give you the idea of E. We need to drill a well which is passing through here or passing through here. Okay, so this is a more difficult scenario. We need further study, we need further modeling to process it. Combining this, so this is a simpler correlation profile. Combining all this, I'm getting back to the simpler petroleum system model. So we get structural model from seismic, we get some depositional model from the geological map or the structural, the seismic itself from identifying the sequence boundaries. You combine all this, you get an entrapment scenario, or you get an occurrence of source to cap rock beneath the subsurface. You can see the stacking of the subsurface, stacking of layers in the subsurface. We can get the pinch out, or you can get many kinds of structures, which is possible in various kinds of depositional models. You can get the idea of source rock, reservoir rock, cap rock. Of course, these are lithologies. You can get the idea of lithology from petrophysical models. We combine all the logs, we combine core data, we combine cutting data with it. You get a basic idea of petrophysics of this source to reservoir and to cap rocks properties. These are property modeling basically. And then we have a migration model where we can identify the source rock. We can have different migration pathways here. These are tiny migration pathways. We can actually identify the high porous, high permeable layers in the subsurface. And then we can map the migration pathways. We can map the entire process with the help of software, where we can get the maximum accumulation of gas, maximum accumulation of oil. And then we can plan further for drilling our well. This is a very beautiful thing. This is easy to understand, but it's very difficult to get there because you need lots and lots of data to get here. When we have all the elements of petroleum system modeled, we get a fifth model called a reservoir simulation model. This is basically what we need right now for the advanced understanding of our subsurface and to reduce our risk to exploration. We have pressure data, production data, and crude oil chemistry. We combine them with these four and we get a reservoir simulation model. There are various methods available. We have GCM modeling. We can have a flow modeling, multi-phase flow modeling. You can get the faults here from this structural model. We can get the various layers here from depositional model. From wells, you can get the petrophysical model, and with the migration model, you can get the accumulation zones. So you can identify the different places and different horizons where we can get the maximum chance of getting the hydrocarbon, right? So let's not waste any time. I will just conclude quickly. This is a basic understanding or model, how it looks like. It's a very famous meme template from Ali Bhatti. He's a very famous artist. And he actually drawn this in a very different perspective. I am using it at a different perspective here. So we start here. We have some basic understanding, but if we continue with this skill and this knowledge, so we'll get something else. Okay, I mean, we'll never get to the clear picture, and never close to the reality. Then we improve ourselves, we improve our skills, we improve our tools, we improve our technologies or methodologies to get here. And then finally we can get some idea of how the drawing should look like, or how, what I'm inferring through the drawing. Now that we know this is a horse, but if I cut the image from here, we don't know whether it is a horse or a cow or something else. So it's a good start with starting with less data. We have less understanding, we have high risk and low success rate, but it's still a good start. We can have data on the way to the exploration, and for that we need to drill more wells, we need to gather more data. We have good progress, sufficient data, some understanding, moderate risk and moderate success rate. We are basically here. We get some insight of the subsurface, but not all. Not all heterogeneities can be revealed at this phase, right? We get further data, further assessment, further studies, and we get excellent progress, more data, more understanding, low risk and higher success. This is where we want to get. Okay, so I am not saying that this should be the entire picture. If we start from here, you can have a beautiful picture of horse all the way around. I'm not telling you that. We should start somewhere very basic, then we need to make progress, we need to gather more and more data, and eventually we'll get there. Okay, so now even if the head is not here, I can understand that this will be a horse head, right, because of this part. So this is interpretation, or this a model should look like. So finishing that, I will conclude with another famous quote by Parker Dickey, famous petroleum geology professor from University of Tulsa. He said, we usually find oil in new place with old ideas. So basically, whenever we are in exploration phase, we have a new place, a virgin area with old ideas. We have some methodologies which are old. We apply them and we get the oil. Fair deal. And sometimes we find oil in an old place with a new idea. This happens when we reach a more mature phase of the basin, more mature phase of exploration. So where we get us an idea, a rough idea of the basin, or we get much of the idea of the basin, but my reservoir is declining. So I have to introduce new technology, new innovation, new methodologies to acquire more and more modeling pieces, right? So we find oil in old place with a new idea. This is also valid, but we seldom find much oil in an old place with an old idea. What does that mean? Because we have already explored the basin and we possess some sort of old type of skill set. You can never get much oil from this. You have to process, you have to gather a lot more data. You have to a model should be evolving, right? A model should not be whatever they believed earlier should not be valid till now. Okay, so a model should be evolving process fed by the data we acquire in the way. So several times in the past, we have thought that we are running out of oil when we are actually running out of ideas. This is, I conclude this summary, and thank you.
Thank you, Orko, for this wonderful talk. It was just an experience to hear from a person directly related to petroleum industry to about the exploration methods, different exploration methods. And thanks for not using the so much jargons. I don't think that the audience here, they are not from particularly from the background of oil industry. They are mostly this video here were present here or will be seeing this or watching this in YouTube later on. Mostly we wish to see the faces from the students community. Okay,
Yes,
so
I have basically targeted it for the students and not much for the professionals here.
yeah, thanks for that. Thanks for that.
It's just for the inspiration of them to getting into oil industry or getting into exploration businesses.
Yeah. So just move on to my question. What I wanted to know from you, like you are a geologist, no?
Yeah, right.
So the basic question comes first: where can a geologist feast himself or herself in the oil industry during the not only the exploration but also in the production phase? So what will be the role of a geologist?
So in the exploration phase, it's fairly easy deal that exploration from starting to end, you always need geoscientist. I will not recommend the term geologist here because a lot more discipline related to earth science are involved in this process, right? We have geophysicists, we have petrophysicists, we have geochemists, we need all together, and let's call them geoscientists. Okay, so from the very beginning of exploration to getting a field where we can actively get oil and we can get the field into production, we always need geologist and geophysicist and geochemist as well as a petrophysicist. I would say from the production phase, we need to monitor the well regularly. We need to monitor our existing wells regularly. For that, we need pressure data. Okay, pressure data is something that is related to production engineers or reservoir modelers or reservoir engineers rather. So there also you need the help of geologists, because the early model is provided by the geologist himself or themselves, right? So if I have some discrepancy in the production phase, if I am seeing the production is rapidly declining, which was not anticipated back then during exploration, so I have a flaw in model. Okay, so I have to explain again that where my model is lacking, or what should we do more to extract oil from this. So there will always be an exploration point of view throughout the field's life cycle. I would say petrophysics are the persons there who are dealing with the rock models and type, but they need some sort of geological knowledge, right? Because only geophysical data cannot interpret the rock models. You need
Yeah.
some kind of core and cutting that I was discussing about that. So every phase you need geological knowledge or geophysical knowledge. You combine them, you work in integration, I would say.
Yeah. So this lead me to my next question. So that my question is here is to you is the skill set that is needed for the person who is working in the petroleum industry for exploration purpose.
Yeah.
Okay, this knowledge what we gather in our bachelor's or master courses, or the industry will teach and educate their workers, their employees. Uh, for the particular knowledge and skill set or the technicalities what you need.
So in India right now, so I would say in the bachelor's and masters, at least in bachelor's, we have some idea about petroleum geology, all this idea about source and reservoir and cap rock. This idea was planted in bachelor degrees, I would say, and nowadays in masters, when we do further advance, when we go to study further or research further, so there we were introduced, at least in many of the institutes, I have seen specialized courses like well logging interpretation, and petroleum geology is a whole gamut of subject. Petroleum, there are petroleum geologists, petroleum engineers, rather I would say the term petroleum engineers. So there also you take some part of geology, some part of logging skill, not I would say how to interpret it, but the basics, right? When you work actually in the field, you would say much of your textbook knowledge will there will be some basic knowledge, but much of them won't work. It will come with experience. So it's tough to teach that into a classroom, because every basin is different, every oil field is different. Yes, textbook examples are obviously there. Even my examples which I presented here, I have chosen those examples which are actually textbook example where we can actually do some easy interpretations. Okay, but in reality the natural heterogeneity or natural complexity is far more great. We need some basic pieces to get there. So as per skill set, I would say uh, it is not very I mean, what to say, suppose we are talking about well logs. We have some interpretation techniques, we have some there textbooks and all. We can learn about well logs basics and their interpretation, but only the textbook examples, right? So that's what we are taught in college. But when you get into field, you have to learn more and more from your basin for your particular field of work, and your knowledge, your field knowledge from there. For the thin section study and SEM study, I believe these are very specialized skills. You need to learn how to make a thin section. In BSc geology, we have made thin sections, but not the SEM ones, right? If we need to make SEM fragments or SEM samples or for EDS study, you need to do XRD. You have to gain some higher skill set, which I believe in India we have in some labs, in some institutional labs where you do further research, but it's not a routine coursework or something.
No, that reminds me of something. I don't work in petroleum. I work in a completely different field. But working during my research work, I found that the knowledge I acquired during my 5 years of geological training in my the college and university. So that build the foundation. Okay, like it's learning a new language. In your college days or school, you just learn to identify the alphabets and learn the basic grammars, and
Right.
how to read
Right.
a complete novel
Absolutely.
in the new language. You should have to acquire this knowledge by reading these books. In your case, by working in the field. In my case, reading new research papers or um, uh, jumping to new research areas.
Absolutely.
Okay, fine. So we would like to now. I would just read out a question from Imad Yasin. So
Okay.
thanks, Imad. I could see you had posted some beautiful questions, and also I would like to mention that Imad has given a very beautiful uh, feedback. Okay,
It's
so thanks,
happening
Imad,
in
for
YouTube,
that.
right?
Yeah.
Because I'm not seeing anything.
You could see it in the in text message in the bottom right corner of your screen,
Yeah.
the third from
Okay, okay.
the
Yes.
yeah.
Now, yes.
So you get the question, but you are seeing it. Let me again read it out for the audience.
Sure, sure.
So first question from Imad is, what are the some of the emerging trends and innovations in the field of subsurface geology and the
Yeah.
petroleum industry, and how might they impact the use of multi-scale data in future?
Okay, right. So the emerging trend, I would say, let's talk about the innovation and the I'm
Orko,
keeping.
just let me interrupt you. We have a few more questions to attend, so I would rather request you to be precise. We are running out of time.
Okay, okay, sure. So emerging trends, I would say, in the petroleum field right now, we are seeing in geological perspective, we are seeing there is a lot more application and lot more opportunities in the geomechanics part. Okay, so the geomechanics part is actually a part of petrophysics that is coming from the well logs. So combining them, we have some model building, and there are various type of models. So from nanoscale to regional scale, as I have discussed. So in these models, you can actually work in different field. You have to work in you need a structural model. You can do cross section balancing. You can you are a sedimentologist, say, so you need depositional models, and you can make the depositional and the dynamic processes literally visualize in 3D. So yeah, I guess these are that. Geomechanics is really a kind of subject that is emerging nowadays. I'm seeing a lot more response from geomechanics part. So they actually calculate the pore pressure, which is very crucial for oil industry, from the well logs. So calculating something, a pressure entity is calculated by some some geomechanical properties or the logs. Okay, so this is very a challenging field. Petrophysics is another term. Petrophysics are now in demand because they incorporate geology and geophysics together.
Yeah.
Yeah. So I guess a question.
Yeah. The next question, I would say it's related to the previous one.
Okay.
You have mostly covered the answer of this next one, which is how do what are the different types of multiscale geological data that can be used to understand the petroleum system, and how are they collected and analyzed? I would rather suggest that you are mostly answered these during your presentation and this
Yes,
question also.
yes, yes. I have shown the
So
various types of data. So these are our basic source of understanding, right? So
yeah,
we have from well log, seismic. These are two indirect source of data, very reliable, but in the same time, well log is basically a single data point is coming from a 6-inch interval. So anything beyond that, you have to go for a core, or you have to go for actual physical samples collected from a core, right? So this is that, and you need to go further. You need to make thin section. Now thin section is not possible for the entire subsurface, or ACM sample cannot be obtained from entire subsurface. We have limitation of money, we have limitation of time, and we need extremely skilled workforce to do that, right? So we have to keep a good balance between our practicality and our source of funds and our understanding. I cannot just, from a nanoscale data. Also, I missed on one point. I can build a nanoscale model or a micron scale model, and I cannot just transport this model all the way to seismic. It will not be feasible. Practically, it will not be feasible because it will need much more computing power for a software itself. Okay.
yeah,
Because I am taking a tiny bit of information and applying it on a kilometer scale volume, so it will not be practical. So I need to upscale my model. Upscaling is done by geologists and geophysicists very regularly, because upscaling means you need to build a block. That's where GCM comes into play. You need to build a block. This block can be meters in dimension. Dimensions are in meters. So you need to build a block where at least you can put all the heterogeneous properties to one homogeneous system. At least you can guess that that block will have similar properties everywhere inside it, right? You build such blocks to explain a bigger seismic model. That will be more feasible. That will be more easy to interpret or easy to calculate. We cannot just do things which should be fancier or which should be better for understanding. We cannot do that. It's not practically feasible.
yeah. So the next question from Imad is, how do the geological processes such as sedimentation, diagenesis, and tectonic activity
Yes.
influence the development of petroleum systems, and how can multiscale data be used to understand these processes? So this I would rather start answering this question. This is nothing like just you have to go to the basics. So these things you are taught in your basic geological courses.
Yes.
Though this is how petroleum generated by the diagenetic processes, and the sedimentary and structural processes, the cap rock and the source rock and the trap section. And Orko, please elaborate this.
So geological processes are what we have been taught in classroom or in further studies, are very basic or simpler models. I said that these are the textbook models. Okay, we have been taught that a reservoir should look like a layer.
Yeah.
Okay, so but it's in reality it's not a layer. It's a combination of thin layers, or it's a combination. Yes, there are bigger reservoirs that we can imagine, which are homogeneous itself within itself. But in practical, where we deal with more complex and more I would say this where more complex and geological processes are involved, in various scale we have this heterogeneity.
Yes.
Right? And
Yes.
we miss one heterogeneity. It is very hard to explain why my model is failing.
Yes.
Because our limitations are our methodology itself, because all the points I have discussed here, be it seismic, be it well logs, be it sedimentary core, be it even SEM, we are always missing something. We cannot negate that.
Obviously.
We are
Obviously.
always missing something, right? Also, we cannot get all the data source from one point. One well cannot provide all the data. Yes, it can, but we don't do it generally. We have multiple wells, we have several data from one well, we have several data set from another well, then we try to combine them into a bigger picture. Okay, so I would say the more the heterogeneity, more complex your model will be. It will be a blessing if we have a simpler reservoir, if we have a textbook example sort of reservoir, then only one or two equation can solve the entire model. But it's not always the case. That's why we need further processing and further model improvement, further map improvement for this kind of things.
Okay. Thanks, Orko. And I will quickly go to the next question, which probably will be the last. I think, because I don't see any other question coming. But let me thank Akanksha Sharma, Miss Akanksha Sharma, for giving her feedback to she's asking more videos on planetary exploration and space explorations. So thanks, Akanksha, for reaching out to us. We will definitely come up with some new techniques and new developments of scientific and technological ideas about space explorations. So coming to the last question posted by Imad, and I will be putting a part of this question here. That first, Imad asked, what are the challenges and limitations of using multi-scale data to understand the petroleum system, and how can these be addressed? So it reminds me another thing, that today we are everywhere in science and technology domain. We are seeing two terms. We are hearing two terms. One is data science,
Yes,
and again another is artificial intelligence. So everywhere you see, here you had data. So now, coming to the data, you as a geologist or geophysicist or geoscientist, rather, what the term you prefer, so in petroleum industry, rather, you collect loads and loads of data.
absolutely.
What triggers you to tell you that now you should stop collecting your data? Okay,
Right.
that you have had enough. So from that you can build a model to go to the exploration, from the exploration to the exploitation phase.
Right. So I can answer this in a one line sentence: when I'm satisfied. Right. So when I'm satisfied means I have a hunger for more data and more preciseness to fit in my model, or but that will not be allowed if my boss doesn't allow me to do that. I cannot do that, right? Because every data point, every source of data has a cost associated with it. Okay, I cannot just go hunting data from all sources and just combine them, build complex to complexer models, and this is just not done. So what happens is, all the data set I have discussed is all the basics. I would say for our purposes, if you understand a reservoir very with very with very well knowledge, well fed knowledge, then seismic and well logs with coupled with some lithological analysis will be enough. I When I go for thin sections and lab data is when I need to do this source rock analysis. When the basic, the first element of the petroleum system is the source rock, right? So actually it's very funny that whenever we are searching for oil, we always try to identify the source rock first. No
Yeah.
source rock, no petroleum system, right? So we have to have this shale sample first. What is my kitchen? This should be my first question. So obviously we need lab data to analyze this problem. But as we move further, we established a reservoir, we established a cap rock, we established some fault system in it, we established a pool, and then we started exploiting our hydrocarbons there. Then comes the real challenge, that we whatever we understood as a simpler model is not simple at all. it's a multi-component system, and we need to understand the different component differently. So no two sands are same in the subsurface. Okay, no two. These have continuities in different layers, but it's not mandatory that two sands are having same properties or something. So I would say the main challenge comes from the data collection itself. So the data collection by I mean it's our responsibility as a professional. Whatever data I am generating, so I am basically associated with this coring and cutting sample analysis or this log analysis because I'm a field going person. Basically, I do this thing on a first hand basis. So the first data I collect from field, the first data before going to the interpretation office is coming to me. So it's my sole responsibility is to cross check the data. Of course, everybody starting from a seismic person to a well logging person is to QC the data, because it is said that garbage in, garbage out. Whatever data I am feeding to the system, it should be error free, it should be contamination free. Otherwise, because I am telling about nanoscale to kilometer scale, if something in nanoscale goes wrong, then my entire model is a disaster. We cannot afford to do that,
Yeah.
right? So the challenge is the more finer your data will be, the more careful you have to be. Okay.
Yes.
So otherwise, the entire construct actually collapses. So
So
this is one limitation actually, I would say. But everybody is responsible for, everybody in that their level is responsible for that QC. It at every level this data will be assessed, and there is not much scope of mistake because we are collecting data from every sources to cross check that, to validate that. That's why I have presented a slide about integration.
yes.
So
Yes.
one data is not enough, one type of data is not enough, one source is not enough. We have to validate it, we have to cross check it, we have to calibrate it with other data. I would be satisfied with a seismic and a well log alone. I would be satisfied. But there are instances where well log cannot explain, well log rather misses a oil bearing zone because it will show your low resistivity zones. Okay, so by quick look log evaluation, I will miss that zone. But when I see that when I core that zone, we can see a oil rich zone. So that part will be missed for some properties, for some maybe some conductive minerals is there. So basically we need to integrate all types of data set, and we need to see the 3D model from all sides. Petrophysics we can have differences in our views. My view will be different from a petrophysicist view. Petrophysicist will say, okay, the oil situation should be this. I as a geologist might feel this is not a right thing. This is something else, or the fault should be like this. The fault should not be like that gentle or that sharp. Okay, so we can have our differences, but we need to come up with a single solution where this model is valid from all aspects, and our ultimate goal is not to generate data or not to interpret data. Our ultimate goal is to identify a volume of oil.
Yes.
So
Yes.
the,
Yes.
so the end of the line is whenever, if a petroleum engineer or a production engineer who is actually developing the field, so if he says that I can only produce this much oil, which is far away from your model, that value is far away from your model. So everybody's assessment is wrong basically. We need to reassess our model and understand what went wrong.
Okay.
The result will tell the
Yeah.
ultimate story. I need
Yeah.
to match the result. Okay.
Yes.
I am not here to do some fancy experiment or to gather more and more data. We need to publish paper or some big research or something.
No.
I need to match the expectations of my client. My client is the production engineer, or
Yes.
the person who I am selling the oil. Okay.
Okay. Nicely said, Orko. We would like to hear from you the whole night. I could rather love to do that about the new techniques and industry, because uh, for me, it's a new thing. It's an alien world. Okay. But this is what leads the world, advance the world. You all know that how energy industry is building up a new world. So thank you, thanks everyone to
I think there is another question from the audience.
yeah, that we could discuss later on.
Oh no,
So
it has.
you want to
I
answer?
have the
Yes,
answer.
there is, yes, there is a
I have the
one.
answer.
Yeah. So the question, let me read it out.
Sure.
So do you think that AI is going to replace the geoscientist job?
So I have been told that ChatGPT has every geological question solutions or so far. It will teach you how to interpret it, how to read it, the theories about everything. Okay, the ChatGPT is already doing that. So I'm not. So it's a smart system, but think of that. I started with a quote: "Oil is found in the minds of men. It's not in the minds of AI." AI can be trained, but imagination, creativity, I don't think it's a basic foundation of AI, on what AI is built. Because I can tell you an example. I have heard this example somewhere else, some other seminar, that ECS log, it interprets the mineralogy, right?
Yes.
So I can feed the dry weight percentage, and the model will tell me the rather the AI or the machine learning process, although it is a supervised or unsupervised, whatnot. So this will tell me exactly a perfect fit for all the percentages into a mineral assemblage, just like normative analysis we have done in our colleges, right? So the data fits correctly, but it says I have pyrite and anhydrite side by side. Okay, geologically it's not possible,
Nothing.
but you cannot argue the data because it fits so perfectly that if you don't know this fact that geologically it's not possible, uh, then you might actually believe that, but the interpretation is wrong and it's made
Yes.
by an AI.
Yes.
So either we need to we need to teach the AI some basic geology, or we need to teach him some philosophical aspects of geology, or we need to leave that model. So that's
Yeah.
my answer.
That's so well concluded. So let me tell all the question came from our director IIREES. So we
That's a
okay.
very interesting question, actually. That's a very
Yeah.
interesting.
So okay. Good night.
Good
Uh,
night.
good night, all. Thanks for joining, and thank you, Orko, for this wonderful talk.
Thank you.
See you.